Hi everyone, this is Brittany. My project focused on how ocean acidification affects corals in the Gulf of Mexico. I picked a few articles from various journals that we're going to take a look at with a focus on what scientists think the future of coral reefs in the Gulf looks like when faced with ocean acidification. Coral reefs are integral to marine ecosystems that are being threatened by many anthropogenic forces, one of which being ocean acidification. We're all familiar with ocean acidification, but in short, the chemical processing of atmospheric carbon dioxide in the ocean creates excess hydrogen ions, which lowers the pH of seawater. Those excess hydrogen ions easily bond with existing carbonate ions, which lowers the overall concentration of those carbonate ions. This decrease then lowers the amount of saturated calcium carbonate minerals in the water, like aragonite, which stony corals build their skeletons from. The reefs in the Gulf of Mexico are made of stony corals, some of which are pictured in that first image. So the unavailability of the materials needed for them to build their skeletons means that the reefs can't continue to grow. Coral reefs provide habitat for countless numbers of marine vertebrates and invertebrates and also have a lot of economic value due to tourism and fishing opportunities. Figure 3 from one of the articles we're going to look at shows all of the different drivers of ocean acidification in the Gulf of Mexico. We can see that the biggest drivers throughout the entire Gulf are rising ocean temperatures, air-sea carbon dioxide exchange, and ocean circulation via the loop current. Other factors have strong influences depending on the location. You'll see up near the coast that all that riverine influx is where that big dead zone is. But in this presentation, I'm going to focus on the air-sea carbon dioxide exchange. So the first article I looked at was this article from the journal Progress in Oceanography. This article, it consolidates a lot of information from dozens of different studies about the different factors that contribute to ocean acidification. It has some sections on how ocean acidification affects different biological systems as well, which I thought was really neat. This quote is talking about how stony corals are going to face hardships due to ocean acidification. Okay, so these two figures are from this article. Um, so figure 4 is the locations where all of the data sets in this article were gathered from. So this article really has a wealth of information. And then figure 1 shows mean Gulf of Mexico surface values from 2014 to 2020 of 6 different factors that contribute to ocean acidification. We're going to focus on pH, which you can see in that little figure D down in the bottom left, and aragonite saturation state, which is down in the bottom right corner, F. So the next article is from Frontiers in Marine Science, and it looks at different stress factors on coral reefs in the Gulf of Mexico. Um, just for some context, this little omega aragonite symbol here refers to the saturation state of the aragonite mineral, which is a form of calcium carbonate. An omega greater than 1 indicates supersaturation, and then an omega less than 1 indicates undersaturation. A lot of recent studies show that calcifying organisms like corals require this omega aragonite to be well in excess of 1, preferably above 3, so that the corals can optimally produce their skeletons. Values lower than 1 can actually induce skeleton degradation. So when that value drops below 1, existing coral reef skeletons will start to degrade. So this article makes a point to explain that warmer waters actually increase the saturation state of aragonite. The formula that I've included isn't from this article, but I thought that it would be helpful to show. It illustrates that the solubility of calcium carbonate has an inverse relationship to temperature. So in this formula, K is equal to the apparent solubility product of calcium carbonate, which varies with temperature. So as temperature rises, calcium carbonate becomes less soluble and the omega aragonite rises. Despite that, increasing atmospheric carbon dioxide and ocean acidification have a greater effect on stony corals than the slight increase of aragonite from the warming waters. This kind of highlights the complexity of ocean acidification and why it's not a straightforward problem that we can solve. So this article looked at a number of factors, and compared the levels of those factors now with what they're projected to be at the end of this century. So this figure shows aragonite saturation state in the Gulf from 2006 to 2026, and it also shows the predicted levels of aragonite saturation state by the end of this century. So we're remembering that anything below 3 is suboptimal, and then anything below 1 encourages aragonite degradation. So we can see the locations of the stony corals here, and that many of those corals are located in spots that are going to see a massive change. And even just this change from 3.5-ish down to almost 2.5 is going to have disastrous effects. So this next article is from the Journal of Geophysical Research, Biogeosciences, and it uses a few different models to anticipate pH changes in the Gulf of Mexico as a result of atmospheric CO2 in the next 100 years. We know that as atmospheric CO2 increases, the ocean absorbs more CO2 to maintain equilibrium. But warming temperatures mean that the rate at which the ocean can absorb CO2 is slowing down, which means more CO2 is staying in the atmosphere. This feeds into the greenhouse effect, which then creates even warmer temperatures. Warming ocean waters create stress for marine organisms, which makes them less likely to be able to survive or bounce back from acidifying waters. And we can see how that these effects sort of create a positive feedback loop. So this figure shows the results of two different models that were used in this article. Um, since pH is a logarithmic scale, what may look like a small change will have huge effects on marine life, including corals. The delta pH from the two models are different, which is a result of the different parameters for the models. This actually is a good way to show that models aren't necessarily a perfect reflection of what will happen in real life. But both of these models do show a change in acidity that would be catastrophic for stony corals. The model they use is something called the Community Earth System model, which includes 40 climate model situations. They have two different scenarios going on here. The RCP 8.5 scenario assumes minimal greenhouse gas mitigation, so almost nothing. And the SSP37 scenario assumes that society is still using carbon-based fuels, but there has been some amount of mitigation. I found it very interesting that the authors of this paper decided to use version 1 of the model for the RCP 8.5 scenario, and then version 2 of the model for the SSP37 scenario. They actually make a note in the conclusion section of the article that the conditions for each version are different, and that should be taken into account when interpreting the results. So again, this is a good example of why models are not perfect. This last article from Frontiers in Marine Science doesn't focus on the Gulf of Mexico specifically, but it goes into a lot of detail of the importance of all reefs across the globe. It addresses some suggestions that deep water corals might adapt to ocean acidification and that coral reefs will somehow migrate to cooler waters, which is extremely unlikely. And it also details some of the economic implications of coral reef degradation. Figure 6 shows past and future sea surface temperatures under historic, natural, and simulated scenarios. This climate model that they used, they had two of those RCP parameters. They had RCP 8.5, which is the same that was used in the last article, and then RCP 2.6, which indicates that there has been, a larger amount greenhouse gas mitigation. So we can see that even with the lower RCP value, sea surface temperatures are still expected to rise in the next century. Figure 3 shows the effect of that sea surface temperature increase on the aragonite saturation state across the whole world. These visuals are modeled at different concentrations of atmospheric CO2. So that 280 parts per million represents pre-industrial levels. 394 parts per million was a measure from 2012. 450 parts per million is expected to be reached in the 2030s based on this model, and 800 parts per million is expected to be reached by 2080 only in the event that no greenhouse gas mitigation actions are taken. So remember here that, any aragonite saturation state value below 3 is suboptimal for corals and other marine organisms that build calcium carbonate skeletons. And then that worst case scenario with 800 parts per million shows values that would most likely induce the degradation of coral skeletons. This last figure, I just really liked the visual. It's showing the actual chemical processes that are happening that take that atmospheric CO2 and, sort of turn it into that calcium carbonate that corals need to build their skeletons. We can also see the link between atmospheric CO2 and available carbonate ions down in that bottom left corner. And then this second figure B, the red arrows pointing to the top right are indicating the current trajectory that we are on towards a concentration of atmospheric CO2 of more than 500 parts per million. So, what do these articles tell us? All of them state in very clear terms that ocean acidification is detrimental to coral populations, and that scientists are predicting that ocean acidification will worsen with continued increases in atmospheric CO2. Each article emphasizes that if anthropogenic sources continue producing carbon dioxide at the current pace, coral reefs will face very serious consequences. The Gulf of Mexico is an understudied area that contains many vulnerable coral populations. Efforts to study coral recruitment and conservation are ongoing, as is the continued monitoring of ocean chemistry. One area that could be explored in future studies is the differences in ocean acidification tolerance in shallow and deep water corals. Ocean acidification affects these two distinct coral populations in different ways, and any insight into those differences could be useful in trying to protect the deep water reefs in the Gulf of Mexico.